This is my screen.
Yes, sir.
So I have given a note for both the cases. N is equal to odd, n is odd, and n is even. Okay. So for n is odd, you see, just I have written one note. So the individual factors, okay, in the expressions, all the product terms, when you multiply all the product terms, it will result z to the power minus n minus 1, okay, or z to the power minus n minus 1 in bracket. So that means z to the power minus n plus 1, whatever the product representation is. So in this case, okay, so if n is odd, so our actually each product, this is one product, bk0 plus bk1 z inverse plus bk2 z to the power minus for each product term. It goes maximum up to z to the power minus 2. Okay. So if such terms are there, each having polynomial order z to the power minus 2, so then we take it as how many number of terms? That is k is equal to 1 to n minus 1 by 2. So this many terms will be, this many products will be there. So if it is this, that n minus 1 divided by 2 number of terms, so power of z will go from how much? You see that net power of z would be, maximum power of z would be minus 2, it is already there in each product, into how many times it goes? Into n minus 1 by 2 times. So that means 2 cancels and you will get minus n minus 1. Okay. This is the maximum order of z to the power minus n minus 1. So this thing you have to keep in mind. Okay. While expressing any while finding the expression in products for n is odd. Similarly, so this is the structure, general structure that you have done. Now when n is even, that time what happens? The general expression is slightly different. General expression becomes, first we take first order term 1 plus b10 z inverse common, then individual product terms. Okay, individual product terms, the format is same, bk0 plus bk1 z inverse plus bk2 z to the power minus 2, and these products will go how many terms? It will go up to from 2 to n by 2. Okay, 2 to n by 2. Okay, this many times it will be there. So how many times it will be there? 2 to n by 2. That means as you have seen, you see, as you have written, as k goes from 2 to n by 2, number of products is n by 2 minus 1, because it is n by 2 minus 2 plus 1. Okay. You have to add 1 because number of turns difference, you take the difference, n by 2 minus 2 plus 1. Okay. So that means n by 2 minus 1. Number of terms will be there. And then that means z to the power minus 2 will go how this many times. So z to the power minus 2 into n by 2 minus 1. That means it is minus 2 into n by 2 minus 1. That means it is minus n plus 2. Okay, minus n plus 2 in the product series. In the first, means in the product terms. Okay, Now, apart from this, one another term is there, that is having 1 plus B10 Z inverse. So the Z inverse further will add one more order to Z, power Z will increase. Okay, so that means Z to the power minus n plus 2 minus 1. So it will become minus n plus 2 plus 1. Okay, so it power becomes, so here it is minus n plus 2 minus 1. Okay, so it becomes, so this will be added. Okay, this will be added, so it becomes, so it is a minus n plus 1. Okay, so this thing you have to keep in mind. So I have given you two examples for case, this is for n odd, okay, n odd, and this is n even. So I am giving you the solution, okay, that I have already uploaded, and it was the last time the students performed. Okay, so for the first one, it is very easy. Okay, first one, it is very easy. Your senior, one of your senior, that is Mr. Nikhil was there, and also many students used to perform this, used to solve, was able to solve this problem. Okay, this time I am again giving you. So for the second problem, you just note down, okay, this is the general expression. Because I am discussing, because otherwise you will not do, okay, and it will not take so much time. Okay, then this into this is the general format. Then this should be equal to this part. Now with calculation of different coefficients B0, B1, then B1, B2, okay, you just go through it, you will get one expression of B0, that is Q. So if you assume B0 is equal to 2, okay, then this is 1. Okay, ignore the, then another value of B0 is this one. So ignore the complex number. So we consider B0 is equal to 2. And finally we get this expression. So they have shown this is a multiplier, but this is not required. Multiplier symbol. You can keep with simple array, a simple arrow. Then you can do it. Okay. Then this another student has performed the same example. Okay. Okay. So you just go through it, and if you don't understand, then you tell me. Have you understood this?
Yes, sir.
Okay. Also try to do yourself. Okay. Then we go to the next topic, that is lattice structure. Okay. The slightly difficult structure, but have some advantages, and actually it is used in speech processing application and adaptive filters, design of adaptive filters. So you know that lattice means what? It is a basic, uh, it is a structured, the whole, this is an atom. You can compare this with some atomic structure, okay, lattice structure, atomic structure. The whole structure is repeated. Okay, some basic or elementary structure will be there, then that structure will be repeated again and again. Okay, and it forms the whole structure. So uh, for that, to understand that, you have to go through the analysis. So let us assume that we are our, and it is actually for FIR structures. Okay, you can implement using IIR structure. We will discuss it later. But since we are continuing with FIR filter realization, it is easy to understand with this lattice structure with FIR realization. Okay. Why you choose FIR? Because it is only all zero system. No pole is there. All zero system, and that represents only numerator terms is there in the transfer function or system function. In the system function, only numerator that consists of zeros, the terms are there. Okay. It consists of zeros and only numerator expression is there. So that system function is say HM or AM. HM or AM. AM is represented in terms of some coefficient alpha m. Okay. Generally, it is actually also polynomial, but we are writing in summation form. Okay. So the values of AM is what? AM is for certain stage. Okay. So sequence. So it is actually what? Sequence of FIR filter with system functions. So one filter is having transfer function AM or HM. AM is the order, so that means m number of stages will be there. At each stage, for a particular value of m, you will have some coefficients. So let us say we have this coefficient mz as 1 plus alpha m k into z to the power minus k. It simply is a polynomial of, or you can say zero. It consists of zeros, or it is a z transform of certain sequence, okay, or it is only numerator terms, let us say. So if it is then here you see that unit sample response. We have earlier discussed that this kind of filter, any filter has the unit sample response HN or H. So that HMK is actually equal to alpha MK, and as we have seen that if you take the Z transform of impulse response, okay, then you will get the system function. So this impulse response is actually the coefficients alpha m k. Impulse response at different time sequence, k is equal to 1 to m, but at k is equal to 0, it is, let us say it is 1. Okay. Now with this expression, we describe that AMZ is the ratio system function with ratio of output to input yz by xz. That is equal to 1 plus summation k is equal to a 1 to m a k z to the power minus k. Okay, this is written from this only. Just we are writing here yz by xz. So if you take xz, okay, in this equation right hand side, okay, then it will see, you will see I have written the expression at the left corner, bottom left corner, that is yz is equal to xz plus this xz will go inside the series, okay, xz into z to the power minus k. Now if you take the inverse z transform, okay, of this expression, then it will become yn is equal to xn plus summation k is equal to 1 to m alpha m k. The coefficients will not change, but since xz into z to the power minus k for each term, okay, for each value of z, so for each value of it is represented as time shift operation. Time shift operation, and in z domain it is multiply the z to the power minus k. So in time domain it is actually x of n minus k, okay, provided summation for each value of k. So this is our expression of output expression of the filter, okay, FIR filter. FIR filter that represents what? It is a its output consists of present and past values of input with coefficients impulse response with its impulse response or coefficient alpha mk. Now this can be represented in different way. One is direct form, okay. So this is direct form realization, that what we do, we pass. So actually it is output is generated with the sum of the input plus sum of the present input plus sum of the weighted past input, so first xn is there, it is passed with one delay element, so it becomes x of n minus 1, then xn is added. So this creates xn plus x of n minus 1 into the coefficients alpha m1. Okay. Then this xn minus 1 again is passed to another delay element, it becomes xn minus 2 and multiplied with this product alpha m2 with the coefficient alpha m2, then it becomes this. So previously the value xn plus alpha m xn minus 1 now added, okay, and this is added and we will get the finally output yn, that is equal to the, according to the expression, this 7.2.1. Okay. This is one structure. Okay. Another structure is that suppose we take xn different way, okay, directly to the output sequence, or here some adder circuit is there, okay, adder circuit we consider as the output. Now this adder is actually calculates the difference between the xn and the predicted value of xn, okay, predicted value of xn. How the predicted value is calculated? Predicted value is calculated, suppose in place of alpha 1, these negative signs were not there, okay, only the positive signs. So we take the previous values of xn, so xn into alpha m, xn minus 1 into alpha m plus xn minus 2 into alpha m2, xn minus 3 plus alpha m into alpha m3. This way we take only the past values of input multiplied with their weights, okay, or impulse response. Then this is also actually what it is, the calculated value of the present input. Present input is calculated from the previous inputs or past inputs with the knowledge of the past inputs. So now present actual input is xn and predicted input is something like this. Here x cap n, say it is coming x cap n. So xn minus x cap n will give you the output yn. This is not exactly yn. It is called actually error between the actual one and the predicted one. Okay, actual one xn and the predicted one. Now since this structure is used for prediction filter, but for our purpose we just keep the signs negative here, and this negatives makes, and also again subtraction is there, minus minus it will be plus, so all are added. So actually indeed it is the output sequence yn, but it can be compared with one predicts FIR prediction filter. Okay, so these are the two kinds of realization of FIR filters. One using normal direct form structure, another is FIR prediction filters in direct form. Okay. Now this is explained over there, what I told, that prediction filter. Okay. Now coming to the lattice structure basics. Okay. So here it starts that let us consider when m is equal to 1. Okay. That means filter order alpha m goes to up to alpha 1. Okay. So in this equation, okay, here 7.2.1 m is equal to 1 means yn is equal to xn plus alpha 1 into xn minus 1, alpha 1 into xn minus 1. Okay. This is your if we, this is the output if we consider it is a single order or first order as filter structure. So your output yn is xn plus alpha 1 xn minus 1. This suffix of alpha 1, that means it is a first order filter. Okay. Or order of the filter is 1. Okay. And this is also k is, this is the sequence for k is equal to 1. Okay. Now say if we assume one constant k1, okay, k1 is equal to alpha 1, okay, or you will see actually it will be called as reflection coefficient k. Okay, this is alpha 1. So we have the equation xn plus k1 xn minus 1. Okay, so you see that the same realization, okay, here where output yn is equal to xn plus alpha 1 xn minus 1. How it is implemented? Xn is this. Now first it is called the initial functions. It is initial functions of any stage. Okay, there will be some input function. Okay, so it starts with f0n, so it will be repeated, you know, as I told. So this original function f01 xn is actually the original function f0n, and g0n is another function which is also equal to xn. Okay, g0n and xn is both are same, but we passed xn in the through the delay line z inverse, so it becomes xn minus 1 or g0n minus 1. So what we get finally, that one xn or f0n in the top line, and the bottom line is delayed version of that. Okay, delayed version of input xn, g0n minus 1. Okay, now both are passed to the same coefficient. Both are multiplied with same coefficient k1. So this output of the adder, output of this adder is what? F1n. This is the output of first stage. Say I will, stage is different thing, but what we are discussing that there is a filter, but we are trying to implement using lattice structure. So for this first stage, f1n is equal to, or yn is equal to what? Xn plus alpha, that what we have got, xn plus alpha into xn minus 1. So what alpha is assumed? Alpha is assumed k. So xn plus k1 into xn minus 1 for f1. This is your main function or required output function yn. But at the same time, we use it through another function. We use another function g1n, g1n, where uh, it is what, so original function is now multiplied k with k1, but the delayed function is not multiplied, it is kept as it is. So out the second output function g1n is k1 f01 plus g0 n minus 1. Okay. So we see that it is equal to k1 xn plus xn minus 1. So f1 is your first output, which is equal to xn plus k1 xn minus 1, and g1n is your second output, but the coefficient is in reverse order, that is reversed. The coefficient k1 goes now to the coefficient of original function x1, xn. So this is called single stage lattice. Okay. Now we go to the second order stage lattice. So that means the we consider the delay of 2 for the inputs. So input goes up to xn minus 2 order delay, or filter order goes to up to m is equal to 2. So in that case, yn is equal to xn plus alpha 2 1 xn minus 1, okay, plus second coefficient alpha 2 x of n minus 2. Okay. This is your filter coefficient. In place of alpha, okay, there are many values of alpha, but coefficients will be different for each and every individual stage. Okay. So for the first case, what the inputs and outputs, the outputs we have got, f1n is equal to xn plus k1 xn minus 1, and the second output g1n is equal to k1 into xn plus xn minus 1. Okay. So these are the two outputs of any lattice structure. Then for the second stage, the structure is same. Okay. So second, actually, it is the general expression for any given structures. Okay. You see that f1n is equal to, no, it is not written here. Better we'll understand later. Okay. So the second stage, actually f2, okay, f2n is actually calculated from its inputs. There are two inputs, f1n and g1n. In the second stage, there are two inputs in the first stage. One is f0n and g0n, where f0n and g0n are equal to x of n. But in the second case, f2n and g2n, where the inputs are f1 and g1, are not same. Okay. Here actually they are coming from the previous stage. So for the second stage, input is for the second stage and first output, main output, we consider input f1 is not changed, but it is there the coefficient k2 in the second stage is multiplied with another input g1 but delayed. Okay, g1 n but delayed. Okay, g1 n minus 1. Then G2n is the second output, which calculates which adds the coefficients K2 with the first input F1 multiplied with F1 plus the delayed version of the another input G1 n minus 1. Okay. So this is the output of the second stage. Now both the stages are cascaded. You can see here that for each stage the constant coefficient is same. Here K1, here K1. This is K1, this is also K1. Okay. So but input is for the first stage inputs F0n, one input F0n, another input G0n. So two inputs and two outputs in all stages. So here for the first stage output is F1n and one output is F1n, another output is G1n, and these are the inputs, two inputs to the next stage. So this is F1n and G1n. Now F2n is equal to yn, that is your desired output. So it is calculated, okay, this way. Now what is the final expression? You can see from the diagram that F2n is what? It is a sum of F1n plus G1n minus 1. Okay. So here we can write that in this expression F2n, in place of F2n, okay, you write in this expression F2n, in place of F1n you write this expression xn plus k1 x1n minus 1 xn minus 1, okay, plus k2 into in g1n minus 1. G1n minus 1 is given, this G1 is given. So now you can calculate G1n minus 1 by, in place of writing n, you write n minus 1. So it is k1 into xn minus 1 plus xn minus 2. So that is written there, that k2 into k1 xn minus 1 plus xn minus 2 is equal to xn plus, now xn minus 1 is common, so it becomes k1 1 plus k2 xn minus 1, k1 k2 xn minus 1 plus k2 into xn minus 2. Now what, this is the output F2n or yn. Now if you compare this lattice, this is actually lattice structures, and K's are called lattice coefficients or reflection coefficients. But you can compare with these coefficients with the direct from structure coefficients. Direct from structure coefficients are what? This is alpha. Okay. So you compare this K with alpha. This K's with alphas. Okay. So we have considered these equations for output yn. Okay. Yn you can see xn plus alpha 2 xn minus 1 plus alpha 2 xn minus 2. Now we compare this with this expression xn k1 1 plus k2 k1 into 1 plus k2 xn minus 1 plus k2 into x of n minus 2. So here we get that k2 is equal to what? K2 is equal to alpha 2, okay, this equation alpha 2, okay, and k1 is equal to K1 is equal to what? Now alpha 2 is equal to K2, and alpha 2 1 is this coefficient of xn minus 1 in direct from 1. Now coefficient is compared with the coefficients of lattice structure, that is K1 into 1 plus K2. So it is alpha 2 is equal to K1 into 1 plus K2. So just by replacing those values, K2 and K1. K2 we get it as simply as alpha 2, but K1, okay, K1 is what? Alpha 2 by 1 plus K2. So in place of K2 we write alpha 2. So once you know the FIR filter coefficients direct from filter coefficients alpha, then you can calculate the lattice coefficients K. Okay. So this is simple thing, but some it is some another important things are there. So finally, what we write that the lattice filter is generally described by the following set of equations, okay, recursive equations. So what? Let me underline this. Or let me put a box over there. So for mth stage output, okay, there are two outputs Fm and Gm, and two inputs Fm minus 1 and Gm minus 1. And each stage there is only one coefficient Km. Okay, this thing you have to keep in mind. Now, overall structure of lattice structure is first stage, second stage, third stage, and each stage this is the basic structure. Okay, input, two inputs and two outputs. One input is directly goes to the summer of the output, at the inputs to the summer, okay, connected at the output, main output, okay, and one input is there that is delayed, okay, first, and it is multiplied with some coefficients, then they are added. Similarly, the other at the output, the second output, it is actually the output of sum of the one input and the and multiplied with coefficient k, with added with the delayed version of the second input. Okay, so this is the basic structure, lattice structure. Now some analysis is there that if, see, to follow these underlined sentences, that if your output yn, okay, yn is your output, but in terms of lattice, your output is, main output is fmn, okay, fmn, it is your main output. Now main output is actually, we can compare with the main output with your outputs yn. Okay, yn is actually the convolution of impulse response and the input signal. So the lattice output can be compared with the same output, that is convolution between impulse response alpha m and the input. So these are the equivalence. Due to the equivalence of FIR filter and lattice filter, we can directly tell that your main output FMN is actually Yn. So since Yn is summation alpha m convolution xn, some convolution between alpha m and xn, so Fm also convolution between alpha m and xn. So now if you take the Z transform of this, so it becomes FMZ is equal to AMZ into X of Z. That is, convolution becomes product or multiplication in case of Z domain. Okay, that we can write. Now, what we saw earlier, that for the earlier means initially when we are discussing the lattice structure, that when the order of the filter was 1, okay, the coefficients alpha was only alpha 1, alpha 1, 1. So it was assumed as K1. Okay. So filter coefficients for the lattice filter that produces F1N are 1, K1. Okay, which was equal to the FIR filter coefficients 1, alpha 1. Okay. This is for normal output or main output F1N, first output of the lattice filter. Now in the lattice, another output is there, that is what? G1, GM. F1 is there, main output. Another output is there, that is GM or G1, a GMN, second output. So in the second outputs, if you go through the equations, okay, you will see it that G2 is what? G2 is nothing but product of this K with F plus G of N minus 1. So here the coefficients, note the coefficients of second output G1. For the first output F1, the coefficients are 1, K, okay, and that is equal to coefficients of direct form structure 1, alpha 1. But for the coefficients for G1, and that is second output, is actually K1, 1, because the coefficients is added and multiplied, okay, from the with the original function. So it becomes now K1, 1. Okay. So actually this K1 is alpha 1, 1. Now look into these two sets of coefficients. Okay. These are actually reversed one. These are actually reversed one. Okay. So we get finally G2N, that is the second output, okay, coming is calculated as this way, that coefficient at the lattice coefficient K2 into the first input F1 plus delay of second input G2N. So this way, if you calculate G2N, its coefficients will become alpha 2, alpha 1 and 1. Whereas the coefficients for the main output F2N is 1, alpha 2, 1 alpha 2, 2. So both are in reverse order. Coefficients of the first output F1 is alpha 2, 2, alpha 2, 1, 1. Coefficients of the second output is 1, alpha 2, 1, alpha 2, 2. They are in reverse order. Now, so we can tell that the coefficients, if the coefficients of the FIR filter coefficients of second output is beta m, okay, beta m, then beta m and alpha m is the FIR filter coefficients of the main output can be correlated. So beta mk is equal to alpha m minus k. Okay, if you compare this, if you see, I have written some notes here that beta 0 is equal to alpha 2, beta 1 is equal to alpha 2 1, beta 2 is equal to alpha 2 when k is equal to 2, k is equal to 0 1 2, this way varies. So this is the relation between beta and alpha. Okay, so this way you can correlate the coefficients between two outputs, okay, of a lattice structure. So now today I stop. All of you have understood what I discussed today?
Yes.